Dr. Hansen here. Life is complicated, especially mine. But life can be explained in terms of very simple monomers, monomeric building blocks which get linked together by very systematic, simple links to make huge polymers, which are complicated. In turn, these polymers can be linked together at many levels of complexity to lead to hierarchical structures such as human beings. So far, I've described this process in terms of proteins, which in an amazingly hierarchical manner can be used to make collagen, or for that matter, the actin and myosin in extremely hierarchical structures can make muscles. Now I want to look at lipids. Of course, lipid molecules are not linked together into huge polymers, but they do stack together hydrophobically to make huge hierarchical structures such as membranes. In order to understand membranes, we want to understand the simple building blocks that underlie them. And in particular, I want to remind you about fatty acid nomenclature, and that's because if you look at the most prevalent lipids by far in the human body, they all tend to have, shown in brown, fatty acids linked to them through, can you tell me what type of bond that is? It's an ester bond. You absolutely need to know that. So most lipids are esterified with fatty acids. And in this video, I want to remind you some of the nomenclature related to them. First, they are fatty. They have hydrocarbon chains. Acids, they end with an acid. Can you tell me why this is called an acid? What about a carboxylic acid? It tends to be a proton donor at physiological pH, and therefore this is very amphipathic. It has an extremely greasy hydrophobic region and an extremely, what will end up being charged head group with two oxygens on it. Carboxylic acids tend to be in the carboxylate form. They tend to lose the proton because by doing so, that allows these electrons in the double bonds to one of the oxygens resonate completely equally among both of them, so that if you have it protonated, the electrons in the bond to the hydrogen and oxygen are constrained into a small region. But when you deprotonate it, those electrons can resonate down, another pair can resonate up, and these electrons can all assume these very large orbitals. The negative charge spreads out, so about 99% of a fatty acid will be in the deprotonated form. Now, why doesn't that happen to a hydrogen on an alcohol, a hydroxyl group? Why doesn't its proton come off? If that proton comes off, the pair of electrons left behind doesn't have anywhere to resonate. In fact, it's nice to leave the proton there to help balance the negative charge. So whereas the pKa of a carboxylic acid is around 4.8, the pKa of an alcohol is around 16. What does that mean? Well, physiological pH around 7.4 is between these two values. Accordingly, since the pH of blood is about 3 pH units above the pKa, the protons will be pulled off of the fatty acid so that there will be about 1,000 conjugate base molecules for every one conjugate acid. At the other end, since the physiological pH of 7.4 is about 8 pH units below the pKa of an alcohol, there will be more than 1 million hydroxyl groups for every one alkoxide. So alcohols, as you can see, really don't want to give up the proton, whereas carboxylic acids really do. Let's now look at the nomenclature of a fatty acid. Can you number the carbons on this molecule using both Greek letters and Arabic numerals? Number one, you look for the landmark. The biggest atoms here are the oxygens. They're both attached to this one carbon, and that will be called carbon number 1. 2, 3, 4, 5, 6, 7. Greek nomenclature? In Greek nomenclature, that's based upon the presence of a carbon-oxygen double bond. That's right there, and the carbon in the bond is called a carbonyl. The adjacent carbon linked to the carbonyl carbon is called the alpha, beta, gamma, delta. What do you think the carbon at the very end will be called? And in fact, at the very end, they kind of do something a little different. They don't completely stay systematic in going through here. What happens to the end carbon? It's called the omega carbon. I am the alpha and the omega, the beginning and the end, right? Have you ever heard of an omega-3 fatty acid? That's referring to having a double bond that's how far from the omega carbon? 1, 2, 3. If there's a double bond here, that would be an omega-3 fatty acid. So let's go a little further with nomenclature, and we'll come back to polyunsaturated fatty acids like omega-3 and omega-6. First of all, I'm not going to require you to know myristic, palmitic, stearic. I will say that in your body right now, palmitic and stearic acid are the most prevalent by far, 16 or 18 carbons in that chain. The longer the chain length is in a given membrane or bilayer, the more hydrophobic interaction will stabilize it, and therefore the less dynamic the membrane will be, the more stable it will be. The presence of a cis double bond leads to a change in nomenclature. So whereas these are saturated fatty acids, they're saturated with hydrogens, this is monounsaturated. It has a single double bonds, which means it's lost 2 hydrogens, it's not saturated. And this particular one is going to be a learning objective, extremely important, called oleic acid. And the double bond causes it to not have a nice, completely linear form. It won't pack together as well. And that's why you absolutely should know that oleic acid is named after olive oil. Olive oil is an oil because the cis double bond prevents it from packing together tightly. Now let's look at chain length a little bit, and we'll come back to degrees of unsaturation. This is absolutely not a learning objective, but play with it a little bit just for your knowledge. Myristic acid has 14 carbons in it, and therefore it's called tetradeca, 4,10-oic acid. If there's 16, palmitic is named because it was found in palm trees and palm oil, and it has 2 more carbons in it, hexadeca, 16-oic acid. How about stearic acid is named stearic because as it gets longer, it's stiffer, it's less flexible, it can form a solid. And that is because with 18 carbons you can do that. Octa 8, deca 10 oic acid, 18 carbons. And then eicosanoic acid is named because ico means 20. This has 20 carbons in it. Eicosanoic acid is also called arachidic acid. And we're going to run into eicosanoids and arachidonic acid in a minute. You notice how I call each of these an acid, meaning a proton donor? I've drawn them with a proton there, but that proton can easily come up to make the carboxyl 8, so then it's N-tetradecanoate, hexadecanoate, octadecanoate. You should know that 8 means it's lost the proton, it's negatively charged, it's oxidized, it has oxygens. Ic acid technically means the proton is still there, but you will not find that nomenclature being used legalistically. If there's a test question sometime where you're looking for hexadecanoic acid and it's not there except in the deprotonated form, you should use that as the answer. Don't work on this too much, just go, I can see the logic of it. That's all I want. But now let's look at adding double bonds. As I mentioned, stearic acid, if you take the same 18 carbons but put 1 double bond in it, it's called oleic acid. Stearic is stiff. It is the most prevalent fatty acid in butter. Oleic acid with a kink in it, with a bend in it, is extremely flexible. It is the most prevalent fatty acid in olive oil. You don't have to add just a single double bond. You could add 2 double bonds or 3 double bonds, and now they're becoming polyunsaturated. I want to be very clear here. When you have a completely saturated fatty acid, that means that every single bond can be trans. The lowest energy conformation is for it to be completely straight. Now, in a membrane, every now and then there'll be rotations going around the different bonds, but statistically, most of them will be straight and they can pack together like soldiers. But as soon as you add a kink, you cannot form this straight form anymore, but rather the kink means there's multiple different ways it can form, and you can never make this trans. Therefore, oleic acid cannot stack together like soldiers, and its membranes will be flexible. Just as you can no longer determine which way this will bend because you put the kink in it, you put a second kink, something's even more flexible. You add a third kink, even more flexible. The more unsaturated a fatty acid chain is, the more kinks you put in it, the more floppy it becomes and the less predictable. Of these polyunsaturated fatty acids, 2 are considered essential. One of them is called linoleic acid, the other alpha-linolenic acid. How can you remember the difference between these 2 names? One of them has 2 double bonds, one has 3 double bonds. Can you tell me which of these is an omega-3 and which of these is an omega-6 fatty acid? Just look at the structures. Alpha, omega, omega-1, omega-2, omega-3. The first carbon with a double bond is the third one. Omega-1, omega-2, omega-3, omega-4, omega-5, omega-6. The first carbon in a double bond is the 6th one, so linoleic acid is a omega-6 fatty acid. Linolenic acid is an omega-3 fatty acid. If you are trying to remember these names, since they are defined as the essential fatty acids, I would look and say the one that is more complicated and more flexible because it has 3 double bonds instead of 2, that name has more syllables. Linoleic, there's no consonant here. Linolenic, there's a consonant there. I'm saying that corresponds with the extra double bond. I don't know how else to memorize that stuff, but it's something to think about. Linoleic acid is called octadecadienoic acid rather than octadecanoic acid. Diene means there's 2 double bonds. You know, from organic nomenclature, ane means saturated, ene means double bond. You may remember that. And I want to remind you that linoleic acid can be converted to arachidonic acid by adding carbon units right at the fatty acid end of it. So you insert 2 carbon units here, you can add double bonds here, and linoleic acid can be used to make arachidonic acid, also known as icosahexatetraenoic acid. 20 carbons, 4 double bonds. Arachidonic acid is a precursor used to make eicosanoids, which are pro-inflammatory signaling molecule. So one of the learning objectives for the talk isn't these specific names, but it's the fact that omega-6 fatty acids tend to be pro-inflammatory, whereas omega-3 fatty acids tend to be anti-inflammatory. And in fact, most of you have probably heard of EPA and DHA. How about icosapentaenoic? Penta, 5-ene double bonds, oic acid. These are omega-3 fatty acids that are quite prevalent in fish, especially salmon, and they're also in breast milk because babies need these things to build their brains. And then we have docosa, so icosa is 20, docosa is 22. I think you've probably heard of EPA and DHA being in fish oil. I am certain your patients are going to be asking you about them. The DHA and EPA are just based upon this simple Greek nomenclature. they're anti-inflammatory. In addition to having omega-3 and omega-6 fatty acids playing signaling roles regulating the immune system, they are also prevalent in membranes. How do you think having a lot of EPA or DHA will affect the fluidity of a membrane? Please stop and answer. So first I'm going to look at a membrane made completely out of saturated fatty acids linked to phosphates. And if you look at that, you can see, wow, like soldiers, they can pack together tightly. If a membrane contains only completely saturated fatty acids, it will pack together extremely tightly and be very steric, very stiff. It will not be very flexible or fluid at all. In contrast, the more polyunsaturated fatty acids with all these cis double bonds that you put into a membrane, the less you will be able to stack together tightly. And so membranes with high amounts of unsaturation tend to be much more fluid. In conclusion, I've described how the nomenclature of fatty acid describes the structure of the fatty acids. In part 2, I'm going to take these fatty acids and link them into more complicated molecules and explain how that relates to life.